it's a very great pleasure to have Netta Engelhardt here to speak. So Netta did her undergrad at Brandeis, graduated in 2011 with a degree in physics and mathematics. She then went off to University of California, Santa Barbara, graduated a PhD in 2016 on Gary Horowitz. She spent 3 years at Princeton as a postdoc before joining the faculty at MIT as an assistant professor in 2019. That's where she is today. So Netta's received a number of prizes for her work, including in 2019, she won the Blavatnik Award for Young Scientists. 2021, she won the DOE Early Career Award and also won the New Horizons in Physics Prize for calculating the quantum information content of a black hole and its radiation. And I think that last thing is going to be what she's talking about today. So I shall shut up and let Netta talk.
Thank you very much, Jeff. And let me just say for anyone who is not familiar with this information that this prize was shared with Jeff. And also 2 other people, Amber Hari and Henry Maxfield. So thank you very much for the invitation. I really wish that I could be at Berkeley in person, but since I can't, I'll just thank you for the invitation and pretend that I'm there. So this talk is about the black hole information paradox, and I've tacked on in the age of holographic entanglement entropy. And I really think that when I say this, I really believe that this is a different age of understanding of the black hole information problem, new tools from the holographic entanglement entropy that I will talk about that have enabled us to understand aspects of this problem and make progress on it, which have been surprising and exciting, and I would argue unprecedented. So I'll begin with just a few questions here, motivational 60,000-foot view questions, and then I'll gradually specialize down 60,000 feet to 30,000 feet to 10,000 feet, and we'll kind of hover over there and not get any closer. So the first question is, what is the black hole information paradox? And I'll spend a large part of this talk explaining what is the black hole information paradox, but at the 60,000-foot level, it is a contradiction between the predictions of gravity and the predictions of quantum mechanics in a regime where the two should not be contradicting one another. Of course, we say that we need quantum gravity to describe the two theories, and it might not surprise you to find that there are contradictions between the two, but this is in particular in a regime where we should not be seeing those contradictions. And I'll say more about what that regime is and why we don't expect that there should be any problem between these two in that regime. The next natural question to ask is, well, why do we study it? And there are many reasons to study the black hole information paradox. One is that any paradox about nature is clearly a lacuna in our understanding of what nature is and what nature does. And we would like to understand it so that we can understand quantum gravity better. Because at the end of the day, quantum gravity describes the interior of black holes, for instance, which thanks to LIGO and the EHT and countless other indirect observations, we know those exist. So as I will emphasize later, without an understanding of quantum gravity, our theory of the universe is incomplete. And with that motivation in mind, let us ask the obvious question, which is, how do we make progress on it? And that will be the subject of most of this talk. So going down to 30,000 feet, what is the black hole information paradox? And just a little bit more detail. So this involves a particular regime. As I mentioned, the fact that we're working in a particular regime is very important here. What is this regime? This is the regime that we call semiclassical gravity, which is the weakly coupled limit of quantum gravity. It's the regime where we expect that an effective field theory, where quantum gravity is more or less just quantum plus gravity, it describes the system very well. So examples of this include, well, the room around you is hopefully well described by a very weakly coupled limit of quantum gravity. Now, we expect that this is valid not just in the room around you and not just on the Earth in general and the observations that we make in our daily life, but also near the event horizons of sufficiently large black holes. This is because the space-time curvature near the event horizon of a very large black hole is expected to be relatively small. And so we don't expect that it's big enough to register on quantum scales. And that means that we expect that this weakly coupled limit of quantum gravity is a very good description of the physics near the event horizon of a sufficiently large black hole. Space-time curvature around where we expect the event horizon of M87 to be is approximately maybe 1 order of magnitude off from what it is near the sun. So we don't expect strong quantum gravity effects to be kicking in at those scales. And the 30,000-foot view of the information paradox is that semiclassical gravity has a prediction which appears to contradict the predictions of quantum mechanics, and that if we wanted to fix it, it appears that we would need large modifications to semiclassical gravity at the event horizon of a black hole, meaning in a regime where semiclassical gravity should be valid and quantum gravity has no business making large modifications. So we have these two theories that contradict one another in a regime where they should really be playing nicely, and where we don't expect that we need any kind of help from quantum gravity to describe the system. So specializing just a little bit further, what is this prediction that semiclassical gravity makes that is so problematic about black holes? And well, semiclassical gravity predicts that black holes can evaporate. And along the way, the evaporation process, from the perspective of semiclassical gravity, appears to violate unitary evolution of closed quantum systems. So this is the contradiction between the prediction of semiclassical gravity and the prediction that comes from quantum theory. I had a missing slide there. Okay, but this is in direct violation of unitarity of quantum mechanics, which we expect is a rather important pillar of our current understanding of quantum mechanics. So now let's move on a little bit to the why in a little bit more detail. Again, the 30,000-foot view of the why. We talked about the 30,000-foot view of the what. So why? Well, information loss, by which we mean violation of unitarity in the process of the black holes evaporating, would essentially be a loss of determinism. It would mean that if you had two different stars that have different compositions that were to collapse into two different black holes and then evaporate, would look exactly the same after the evaporation process. And in particular, that means that if we just had access to the end product of the evaporation process, we would not be able to deterministically evolve it backwards to tell which one of those, which stars which collapse process resulted in what. And that's a loss of our ability to post-dict the past. It's what I would say is a catastrophic loss of determinism if we had information loss. And so even though we don't really get to decide what nature does, it would be rather important to see that black hole evaporation does not in fact violate unitarity, and that physics is in fact deterministic. As I mentioned before, we're pretty sure black holes exist. We've had many indirect observations. We now have more direct observations in favor of the existence of black holes. So nature certainly has a definitive answer to this. And without us figuring this answer, there are phenomena in the universe that we just don't have a complete description of, such as the black hole interior. So if we would like to have a complete description of the universe, at some point or other, we're going to have to confront the black hole information problem. Either way, ultimately, this paradox has a lot to teach us about quantum gravity, and that's the real reason why we pursue it. So a little bit about this age of holographic entanglement entropy. There have been a lot of exciting developments, especially in the last 2.5 years, on the black hole information front. And that's really because there was a catalyst that changed a large number of our approaches in the way that we think about it. So what is it that changed between 2019 and now? So then, meaning pre-2019, which is not that long ago, but again, things have shifted a lot. The conventional wisdom was that if you wanted to see any evidence of information conservation, if you wanted to do a particular type of calculation which is consistent with unitarity, you needed to have quantum gravity. You needed a direct formulation of quantum gravity on hand. That was the conventional wisdom. And furthermore, that semiclassical gravity is inconsistent. It's just not consistent with unitary evaporation. There's no semiclassical gravity calculation that you could do that would be consistent with unitary evaporation. And more recently, since 2019, what changed all of this was a purely semiclassical analysis, an analysis that only used semiclassical techniques, even though there's a bit of an asterisk there, that was consistent with unitary evaporation. And that gave us a bit of a paradigm shift and gave us a new set of tools to use to understand the problem better. And just to emphasize that this really was a change in the way we think about things, I think it's safe to say that most of us thought that it wasn't possible. At least I certainly did not believe that it was possible to do a calculation in semiclassical gravity that would be consistent with unitary evaporation. And of course, I've never been happier to be proven wrong. So I'm going to really begin this talk, since I haven't really done it so far, with a more detailed description of the black hole information paradox as it stood before these new calculations. And then I'll talk about this age of holographic entanglement entropy. In other words, the new tools that came about that were so critical to these new calculations. And then I'll talk about the new calculations, and I'll speculate a little bit about where I think we're going with this in the coming years. So I'm going to briefly pause for questions if there are any clarification questions at this point. And if not, I will go ahead and continue. So our story really begins with thermodynamics, which is the way, in my opinion, most good physics stories begin. So this is a very famous experiment by Wheeler's Gedanken experiment. Now, to understand this experiment, you have to know one thing about classical gravity, which is the so-called no-hair theorem, or no-hair conjecture, if you like, which is that black holes in classical gravity have no microstates. And what we mean by that is if you know the mass, you know the charge, you know the spin of a black hole, then that completely fixes the black hole interior within classical general relativity. Now, Wheeler's Gedanken experiment was the following. Suppose you take a hot cup of tea, which has entropy, and you throw it into a black hole. Well, black holes have no entropy. If they have no microstates. If they have no microstates, that means they have no entropy. Now you take this hot cup of tea, which definitely has entropy, and you throw it into the black hole. And once you've thrown it into the black hole and it got swallowed up by the black hole, well, the black hole still has no entropy, and you've decreased the entropy of the universe. And in fact, you can keep on decreasing the entropy of the universe arbitrarily large amounts if you like. And as an answer to this, I'd like to bring up my favorite quote in physics, which is by Sir Arthur Eddington, which is, if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. And I always visualize black holes like laughing at our expense at the thought that we, had some understanding of what they were. So this was something that bothered Wheeler, and he certainly did not want general relativity to collapse in deepest humiliation. And this story goes, and I shouldn't say that it's necessarily the way it went, but that's how the story goes, that he decided to give this problem to Jacob Bekenstein. Now, whether Jacob Bekenstein decided to take this problem or whether Wheeler decided to give it to him is a matter of some debate. But at the end of the day, Jacob Bekenstein was a student, and he worked long and hard on this problem, which should hopefully be inspiration to the graduate students in the audience. And he came up with a brilliant proposal. So Bekenstein's proposal was that black holes actually do have an entropy. They are thermal, they have a temperature, and they have an entropy. But this is not a consequence of classical gravity microstates. It's a consequence of quantum gravity microstates. And Bekenstein further proposed that the entropy of a black hole is given by the area of its event horizon over 4 in Planck units. Now, we call this the Bekenstein-Hawking entropy rather than just the Bekenstein entropy. And it's very fortunate that there is a BH here, which could either mean black hole or Bekenstein-Hawking. Now, the reason we call this Bekenstein-Hawking is, in fact, this proportionality constant was computed by Hawking, who actually was the one who computed the temperature of the black hole. Bekenstein predicted it, and Hawking actually computed it. It was inversely proportional to the mass of the black hole. I want to emphasize at this point that quantum corrections are really critical here. So black holes in classical gravity don't have an entropy, they have no microstates, and in particular, they're also perfect absorbers. which means that they don't radiate and they're not going to have a temperature. So the fact that we are including quantum corrections here is critical, and this is something which is going to be true in quantum gravity, but not true if we're working purely in classical gravity and ignoring all quantum corrections. All of this is coming from quantum gravity. Now, we finally get to evaporating black holes. So if you have a black hole and it has some temperature, well, if it's got a temperature, then it's going to radiate. And if its temperature is larger than the temperature of its surroundings, then it's going to keep on radiating away energy and mass. And so as it radiates, its mass decreases, and well, its temperature is inversely proportional to mass. So it's going to keep on evaporating until, well, maybe it explodes. Hawking's paper was titled Black Hole Explosions. So this is the very brief 30-second summary of black hole evaporation. Now let's take a look at some numbers. So Sagittarius A star, based on its estimated mass, has a temperature, a Hawking temperature of approximately 10 to the minus 14 Kelvin. Solar mass black hole has a temperature of approximately 10 to the minus 8 Kelvin. These are very cold. Remember, the larger the black hole is, the lower its temperature. A lunar mass black hole would be at equilibrium with the cosmic microwave background. And finally, a coronavirus-sized black hole would be quite comfortable at room temperature. So let's talk a little bit about black hole evaporation and collapse. So here I've drawn a picture where we have time running up, as we do in relativity. And we have some star here. I know it looks not very exciting star, but it's about to be something very exciting. Here, this is just meant to be a ball. As time moves forward, this ball is going to, this ball is going to collapse under the force of its own gravitational field. And as it collapses, eventually it's going to form an event horizon. You imagine this is a sphere, so eventually it enters its own Schwarzschild radius, and the end event horizon will form. And black hole will collapse until it forms a singularity here, which essentially crunches everything down. So this is the picture of black hole collapse. Of course, we're really interested in black hole evaporation. So here we have a number of entangled particles, bell pairs, if you like, that are floating around in our space-time. And we can imagine a situation where we have a pair that nucleated, where one partner is behind the horizon and one partner is outside of the horizon. This is sort of caricature of the behavior of quantum fields around a black hole space-time. Well, this orange one can certainly go off to infinity, and in some sense, that's a way of thinking or modeling the black hole radiation. So black hole radiates, black hole shrinks, and eventually black hole potentially explodes. So who knows what the process actually looks like at that point. So here is again a time picture where we move upwards in time. The event horizon is shrinking. These are the two particles I discussed, and eventually the black hole gets very small and very, very hot. And again, the paradox is that semiclassical gravity appears to imply that information is lost as a consequence of the evaporation process. Now, that's all well and good, and it's nice to have pictures, but how do we actually diagnose non-unitarity? What's a quantitative measure that we can use that's easy to calculate or potentially calculable that we can see, can look at in the evaporation process? And there are a number of such things, but one that we like in particular is the von Neumann entropy, which is minus trace of rho log rho for a density matrix rho. Why do we like it? Well, for one, it's invariant under unitary evolution. So that's pretty nice if we're looking to diagnose unitarity or non-unitarity. It vanishes for a pure state and only for a pure state. So if we start out with a pure state, we would like to end up with a pure state. That means that our entropy, our von Neumann entropy, had better start out at 0 and end up at 0. And it's bounded from above by the thermal entropy, which is also called the coarse-grained entropy. Okay, so we have this quantity. Now, in what sense can we think of where does the word information loss come from in terms of the entropy? This is very rough intuition, but hopefully it grounds some things here. So the information in a state rho can, in a very, very rough way, be quantified in terms of the difference between the thermal entropy and the von Neumann entropy. The larger this difference is, in some sense, the more information you have in your state. And the way that we think about this is that the thermal state has essentially no information content. And that's as you evolve to progressively larger von Neumann entropy, you're getting progressively closer by some measure to the thermal state, which maximally mixed state, which is essentially has no information content. So this is the way of saying information is lost. If we're getting progressively closer to being maximally mixed, then information is lost. Now, this happens all the time in open systems, right? You can have some system, it interacts with its environment, and well, eventually the system is going to be maximally mixed with its environment and information has been lost. And that's fine. We see that all the time. There's no problem with it. But of course, we don't think that the entire universe is an open system. So we don't expect that the evolution of the universe results in information loss. At least we certainly hope not. So let's take a look at a toy model. This is very much a toy model, but it does get some of the ideas across. So let's take an entangled pair, a Bell pair, Alice and Bob. So here we have Alice and we have Bob, and together they're in an entangled state. So here together they're in a Bell pair. Now, so here is a state. If we're just interested in Bob by himself, well, we have to trace out over Alice's degrees of freedom. And that gives us this density matrix here. We cannot represent this as a state as a vector in the Hilbert space. This is a density matrix. And it's actually just a maximally mixed state. And again, this is obtained by tracing out Alice. We're just interested in Bob's state. Now, in this toy model of this Bell pair, the initial state of the pair is pure, just the state psi of the Bell pair. Now, after the black hole is finished evaporating, the final state of the Bell pair is just the state of Bob because Alice doesn't exist anymore. And so S final is just S Bob, and S Bob is log 2, not 0. And so we find that information has been lost since entropy has increased. The entropy of Alice and Bob went from 0 to log 2 since Alice is no longer a member of the system, since Alice is just gone from the universe. And so in this toy model, we see that the system was not evolving unitarily. A little bit more accurately, let's suppose the universe starts out in some pure quantum state psi. You can do this just as well if the universe starts out not in a pure quantum state, but it's pedagogically easier to talk about a pure quantum state. So the universe starts out in some pure quantum state psi. Then we're going to imagine forming a black hole in this universe in the pure state. And we are going to compute the von Neumann entropy of the exterior of the black hole. Okay, well, starts out at 0, but then it's going to increase. Right, we're looking, the black hole exterior is an open system. Its entropy is, we're going to have exchange with the black hole. So the entropy can increase, fine. Now, this is essentially Hawking's calculation, or a reflection of Hawking's calculation. And the entropy begins to increase, and then it keeps on increasing. And it increases and increases and increases until eventually it plateaus at the thermal value. Here it is in pictures. So here we start out before the black hole is formed. We have some star. Then we have the collapse. Event horizon forms. Now we can compute the entropy during this process. That means we're now computing the entropy of everything outside of the black hole, which is everything outside of the event horizon. So this is a moment in time corresponding to this time slice. Eventually the black hole disappears. And we compute the entropy over here, and we find that over here is the entropy, the thermal entropy or the entropy of the maximally mixed state. Okay, so now we're getting close to actually stating we're going to state the actual problem. So you could state it like this. The post-evaporation state appears to be mixed by Hawking's calculation. The product of the evaporation process is a mixed state. The von Neumann entropy of the black hole exterior is mixed. Okay. Standard quantum mechanics tells us that the evolution of the entire universe, its closed system, is going to be unitary. And so the von Neumann entropy of the entire universe is the von Neumann entropy of this state evolved with a unitary. And that's just because von Neumann entropy is invariant under unitaries. That means that it's just going to be the von Neumann entropy initially, which this was a pure state, so this is 0. Now the conflict here is that, or one of the conflicts, so one way to frame the conflict is that, well, the von Neumann entropy of the entire universe post-evaporation is the same as the von Neumann entropy of the black hole exterior. And so we find that it has to vanish, but at the same time, it's greater than 0. So this is one way of seeing the conflict, but as we'll see, the conflict actually appears earlier than the post-evaporation state. So here we have the problem. The von Neumann entropy of the exterior is larger than 0. It's equal to the von Neumann entropy of the entire universe once the black hole is finished evaporating, but the von Neumann entropy of the entire universe once the black hole is finished evaporating should be back down to 0. Okay, so one more slide. So what should we actually get? If we had a unitary evolution, what would it actually look like? Well, if it starts out at 0, then it has to end up at 0. And that means that the actual behavior of the entropy in the unitary evaporation process would have to turn over at some point and go back down. And so you'll see that the conflict with unitarity begins not at the evaporation point here, but already much earlier on, about halfway through the evaporation process. At that point, we start seeing large deviations between what Hawking appeared to see and what the unitary answer would be. So which of these is the correct curve for quantum gravity, and how do we calculate it? Well, this leads me to the set of tools that we need to develop, the advent of the age of holographic entanglement entropy. So a little bit of a preview before I get into those details. Hawking's calculation is extremely robust, and it's sort of hard to, it's very hard to see where his analysis goes wrong. Do we need input from quantum gravity to figure this out? Sure seems like it. Well, what do these new developments do for us that is surprising? Well, as I said before, the new developments were a completely semiclassical calculation of the page curve. But when we say completely semiclassical, we really mean the tools that we used. There was indirect input from quantum gravity. And in some sense, that's what allowed us to make this leap to actually computing a unitary curve for the entropy, so-called page curve, named after Don Page. What is this indirect input? The indirect input from quantum gravity is holography. So let me briefly talk about holography, since the age of holographic entanglement entropy kind of calls for a definition of holography. So in just one slide, holography is a duality between quantum gravity in a box, in sort of an infinite box, an anti-de Sitter space, it's a duality between that and a lower dimensional non-gravitational quantum field theory, typically a conformal field theory that we call the CFT. Now, this is an extremely powerful statement for us because there are many things that we understand much better about quantum field theory than we can possibly understand right now about quantum gravity. And that means that this duality means that everything that we can want to compute about quantum gravity, we could compute in quantum field theory. The challenge, of course, is finding the dictionary that relates the two of them. Now, two terms that are going to come up a lot, the ADS quantum gravity in the bulk, we typically call, it is quantum gravity, we typically call the bulk. And the quantum field theory, the lower dimensional non-gravitational quantum field theory, we typically call the boundary. And I'll sort of be using these terms for the rest of this talk. Okay, so one thing holography gives us, which is incredibly valuable, is that a black hole is just another quantum system. Right? A black hole is just a state of quantum gravity in untitled Sitter space, black hole in ADS. And the duality tells us that's just some quantum state of some non-gravitational quantum field theory. Just an ordinary non-gravitational quantum system. So a black hole is an ordinary non-gravitational closed quantum system, and ordinary non-gravitational closed quantum systems evolve unitarily. So therefore, ADS CFT immediately tells us that black holes evolve unitarily. The black hole evaporation process is in fact unitary, and information is not going to be lost. And I guess we can celebrate that a universe is in fact deterministic. So are we done? Is that it? Can we go home and say we're done? We understood quantum gravity? You know, not quite. ADS CFT has been around for a lot longer than this recent calculation. This is not satisfactory. We want to understand, how does quantum gravity preserve unitarity? There's a lot that we don't understand. We're just being handed this answer, being told that it's unitary. We want to understand, how does quantum gravity preserve unitarity? Sorry, just one more. Yeah, we want to understand better, what is the mechanism by which this comes about? Is semiclassical gravity valid at the event horizon? These are all questions that we would like to understand better. So how are we going to go about answering this? What is the idea here? Well, we know that the usual formula in the bulk, if we just do Hawking's calculation in the bulk, we compute minus trace rho bulk, log rho bulk, meaning we're not doing anything novel, we're just computing, doing exactly what Hawking did in our gravitational theory. We're going to get the so-called Hawking curve, the curve that goes up and then plateaus, information loss. This picture is identical to the one I gave before, except now I wrote rho bulk here. So literally nothing has changed. We're just labeling things a little bit differently. We don't expect to get a different answer. We expect that if we do this calculation the way Hawking did it, except now we're working in ADS, which has some complications, but we can do it, then we're going to get the same answer, information loss. But in the meantime, on the so-called back of the soup can in the dual theory, if we just compute the entropy, we're going to find that it's unitary and it's going to be the same before and after. So information is going to be conserved if we work with the dual quantum field theory, and it's not conserved if we work with the semiclassical approximation to quantum gravity in ADS. Okay, so what do we have? We have a non-gravitational calculation of a unitary entropy. We have a gravitational calculation of a non-unitary entropy, which to me is the perfect realization of the principle of conservation of misery. So how do we get around this? Well, what if instead of using minus trace rho bulk log rho bulk, we used a holographic prescription? In other words, we used a holographic dictionary for computing minus trace rho boundary log rho boundary. In other words, we were to take this quantum field theory calculation and use the ADS CFT dictionary to figure out how to do it using gravity. In principle, that could give us a unitary answer for a gravitational calculation. And remarkably, it does. So here are the two different options that we currently have. We have a geometric non-unitary calculation that we can do, gives us the Hawking picture. We have a non-geometric unitary calculation that we can do, which would give us consistency with unitarity. Now, what we'd like to do, of course, is option 3, not options 1 or 2, which is that use the holographic dictionary to mix these two up. We want to do the calculation in this one using the language of this one. All right, so again, the idea is to compute the so-called the unitary page curve using this language. So how do we go about doing that? Well, we need a holographic prescription for computing the von Neumann entropy of the boundary theory. And the way we do this is using the so-called quantum extremal surface calculation. What is this? Well, it's what relates the von Neumann entropy of the boundary to geometric quantities in the bulk. What is a geometric quantity? Well, it's the area of a particular distinguished surface. I'll explain what it is in a moment, over 4 Planck units. So this looks a lot like the Bekenstein-Hawking entropy, plus the von Neumann entropy of quantum fields outside of the surface. So here we have a surface. This is a single moment in time. We compute the area of this over 4, and then we add to it the von Neumann entropy of everything outside of the surface. And this quantity is, it appears enough in the literature that it's gained a name. It's called the generalized entropy. This was coined by Jacob Bekenstein. Now, of course, we could potentially have many different surfaces we could do this calculation for. And you'd say, well, you get a different answer for every different surface, so how do you know which one to use? Now, the surface that we use is called quantum extremal. And roughly speaking, what that means is if you take the surface and you slightly wiggle its location, then its generalized entropy, the sum of the area and the entropy, doesn't change to leading order in this perturbation. So it's a stationary point of this functional here, the area over 4 plus the von Neumann entropy. So this is what we put into this calculation. And one important point is that you may have multiple such surfaces that are stationary points of the generalized entropy functional, multiple quantum extremal surfaces. And if so, then you use the one with the smallest value of the generalized entropy. So this is the prescription that allows us to go from a boundary entropy, which should evolve unitarily, to a bulk calculation, which we can do geometrically using the gravitational semiclassical gravity language. And so let me now finally tell you about this calculation. So these are based on 2 papers, one by Jeff and one by myself and collaborators. So here we have an evaporating black hole. We're going to take an evaporating black hole in ADS. There is some subtlety and complication there that I won't really go into, but we have to kind of force the black hole to evaporate, but we can do that. Okay, so what happens through this evaporation process? Well, initially, the quantum extremal surface of interest, the minimal quantum extremal surface, is the empty set. So that's the one whose generalized entropy is smallest. And so you take the area of the empty set, which shockingly is 0, and you get a contribution from the von Neumann entropy of the bulk quantum fields. And with time, this von Neumann entropy grows. And we expect that both the Hawking curve and the Page curve initially have an increasing entropy. Now, about halfway through the evaporation process, there's a new quantum extremal surface that nucleates, appears in our spacetime. So here is a surface chi. It lives behind the event horizon. So here it is at a moment of time, and here it is over here. Now, as we evolve forward in time, the generalized entropy of the surface chi is in fact decreasing. And it is that generalized entropy that gives us the turnover in the Page curve. The generalized entropy of this new quantum extremal surface, which is actually minimal, in other words, it has smaller generalized entropy than the empty set. So we get this increase here, but we also get a decrease exactly as we expect. And so this gives us a calculation of the Page curve, a curve which is consistent with unitarity. And it is obtained using only semiclassical physics in the sense that we can compute an area and we can compute the entropy of these quantum fields using only effective field theory. We don't need to use quantum gravity in this calculation, except in the interpretation of this formula and via the ADS CFT dictionary. So this is extremely exciting. Let's take a step back and understand what happened here. So here we have this relation between von Neumann entropy and the area of a surface plus another von Neumann entropy. Now, what happened over there? The fact that this is computing the entropy of quantum fields outside the particular surface, and we also have the area of the surface, this interplay between the two and the definition of the quantum extremal surface appears to be what saves the day. Because if we just use the von Neumann entropy, we know that we would get an answer which is not consistent with unitarity. That's just a Hawking calculation. Now, as I mentioned just a slide ago, the only place where quantum gravity appeared is in the interpretation of the generalized entropy as the entropy of the radiation. That's the only place where we needed to use quantum gravity in this calculation. And of course, as much as we would like to celebrate and say that we've seen evidence of unitarity using only semiclassical gravity, this brings up at least as many questions as it gives answers. For one, why does this work? Why does quantum gravity repackage entropy in this way? And what microscopic Planckian physics is responsible for the success of this formula? Well, I'm going to talk a little bit about some progress on this front towards understanding better where the quantum extremal surface formula comes from, why it's successful, and what does it mean for the information paradox moving forward. So to understand this, let's ask the question of how do we generally compute the von Neumann entropy? Forget gravity, let's just talk about ordinary quantum mechanics. We want to compute an entropy. How do we do that? One way to do it is using the replica trick. So minus trace rho log rho, we can rewrite via this replica trick here. What is the replica trick? Essentially, it means you introduce n copies of your system, replicas of this. Again, we're working with a non-gravitational theory here. That's rho to the n on this n copies, and then we use this identity, and we could do a computation. So that's a very valuable trick. Okay, just a trick. So where do we go from here? Well, we actually have a pretty decent understanding of this replica trick in holography. We know how to relate trace rho to the n to the so-called gravitational path integral, which is essentially exactly what it sounds like. It's an integral over metrics where you set boundary conditions for those metrics. So very similar, but also very different in some ways from the usual path integral. So we know how to relate this object, trace rho to the n, or trace rho in general, to the gravitational path integral. And if you then essentially plug this into the replica trick for the von Neumann entropy, you can actually justify the new quantum extremal surface formula, the new quantum extremal surface, the one that gives you the downturn in the Page curve that leads to unitarity. But there's a cost here. There's no such thing as a free lunch. These n replicas have non-trivial correlations. So here I've drawn what we affectionately call replica wormholes, which are correlations between these n apparently independent copies of the same system. So these are n independent copies of a single quantum theory. How can they be correlated? Well, I would say there are several different answers at this point. We're not 100% sure which one is correct, but that's what makes it part of my section of the information paradox moving forward. So I would say there's only one example where we really understand what's going on 100%, or at least 99%, which is two-dimensional dilettante gravity, where we know that the gravitational path integral computes a disorder average. There's an analogous phenomenon for the condensed matter theorist in the audience, the condensed matter experimentalist in the audience, that appears in spin glasses, where you have some system that appears to inherit correlations between the replicas as a consequence of averaging. I have more to say about this. If you're interested, please ask during the Q&A. But in more general theories of gravity, I would say it's still not clear exactly what this means. So it's possible that we have an ensemble average more generally, but then what are we averaging over? There's reason to expect, and from ADS-CFT, that sometimes there is an exact theory. Maybe we're not averaging over theories, maybe we're averaging over states. Maybe there are some non-perturbative corrections that come in to offset the average, these correlations between the replicas. There's been a lot of work on this, and I would say arguments in favor of all of the above. So at this point, not clear, but what I would argue is clear is we have a new understanding of a key ingredient in the resolution of the information paradox, which is the gravitational path integral, which appears to know a lot more than at least I originally gave it credit for. I would argue that we have to understand why it's dominated by these correlated replicas, why they give rise to unitary evolution, what these contributions mean for the gravitational theory. If there's averaging, what is it averaging over? If there isn't averaging, how do we explain these correlations? So what is the current state of the information paradox? If I had to summarize in one sentence, I would say we haven't solved it yet. But at least I would say we're closer. So a few questions that I think are important that we're thinking about right now, that I'm thinking about right now. What entropy is the quantum extremal surface actually calculating? If we wanted to calculate directly from the formula minus trace rho log rho in the quantum gravity theory, how would we do that? What does an observer outside the black hole actually measure? If I were very powerful and I could collect all the radiation, I could just put it through a quantum computer, what would I see? Arbitrarily powerful quantum computer too. Is the path integral doing an averaging of some sort? What are the internal dynamics of an evaporating black hole? Why do they scramble the information in this particular way? How do we decode the information? And to me, most exciting and most interesting, where did Hawking go wrong? What was the mistake, or what was Hawking's calculation missing? And so with that, I will close. Thank you very much for your attention.
Okay, thank you so much, Netta, for that wonderful talk. Really great. I'm sure I speak for all of us. I guess we should turn to questions. So let's see. Sorry, did someone say something?
No, that was me. I was just saying, I think there were questions. Yeah.
So there were a couple of questions during the talk that I decided not to mention to you because it seemed like they would throw it off. We also have some people's hand raised. So the people who asked during the talk, okay, let's see. In the Q&A, there's a question of, is there any interpretation that a real wormhole appears to connect the radiation in the interior of the black hole? In other words, ER equals ETR.
That's a great question. So it depends on what you mean by interpretation. So there were some models that people constructed with an extra holographic dimension. So now we're talking about holography within holography, in which the real wormhole did appear to connect the radiation to the interior of the black hole. But more generally, I mean, those are sort of very special cases. More generally, I would say that ER equals EPR doesn't, strictly speaking, require the wormhole. Okay, there's an interpretation of ER equals EPR that doesn't require the wormhole to appear so much as that it is possible to act with a unitary on your system to produce another system in which the radiation is connected to the black hole via an Einstein-Rosen bridge. Now, there's been some work on trying to realize this and seeing that the system is unitarily equivalent to one that has an Einstein-Rosen bridge. I'm actually working on this right now myself, but so there is a sense in which these wormholes are related. They also have a similar factorization. There's a factorization problem in one and also in the other, but I think it's not. I would say it's not 100% clear to me what the exact relation is between these correlated replicas, these replica wormholes, and the Einstein-Rosen bridges. There's clearly a relationship, but I don't think it's 100% clear right now what it is.
Awesome. So there's a question that was just asked in the chat, which is basically your system description is entropic, that is pretty much omitting the microscopic degrees of freedom as thermodynamics omits the microscopic degrees of freedom. Do you have any hint of an alternative approach that takes into account some microscopic degrees of freedom that are partly omitted by entropic approach?
So I would not say that I guess it depends what you mean by omitting the microscopic degrees of freedom. So the entropy we're computing is certainly not a thermodynamic entropy. We are computing a fine-grained entropy here, not a coarse-grained entropy. We're computing the actual von Neumann entropy of the system, not the thermal entropy. If what you mean, so that's what you mean, then I would say, no, we're not omitting anything. But if what you mean is that we are looking at the semiclassical description of the system, rather than the quantum gravity, the full microscopic quantum gravity description of the system. And therefore we're seeing some coarse-grained version of it. And the quantum extremal surface formula essentially is a machine for taking this coarse-grained description, this emergent space-time description, and churning out the right answer. Then yes, then I would say that we do have some microscopic degrees of freedom that are missing, which is the fundamental degrees of freedom of quantum gravity. An alternative approach that would take into account this microscopic degrees of freedom essentially is trying to understand, and that's what gravitational path integral is kind of trying to go, in a sense, is trying to understand what is the origin of the quantum extremal surface formula and why it works.
So there's another question in the Q&A, which is someone saying they'd be interested to hear about the connection you alluded to with spin glasses.
Yes, I'm so glad someone asked. So yeah, so these correlated replicas seem very analogous. The replica wormholes seem extremely analogous to the correlated replicas in spin glasses. And of course, in this case, we're computing the replica trick for the von Neumann entropy. And for spin glasses, we typically compute the replica trick for log z. But the phenomenon, at least in 2 dimensions, appears to be extremely similar. And in fact, with a couple of collaborators, Sebastian Fischetti and Alex Maloney, we actually decided to investigate whether the same type of theory, this 2-dimensional gravity that has ensemble averaging and has these replica wormholes, whether it also has a similar spin glass phenomenon where log z is actually dominated by replica wormholes. And in fact, there is a regime where that is the case. And so what we found is very similar to spin glasses in the sense that the annealed free energy in these 2-dimensional gravity theory was non-monotonic at low temperatures. And if you add the correlated replicas, if you consider the contribution from replica wormholes, then you actually find that this is ameliorated, but not fixed entirely. And so far this sounds a lot like the Sherrington-Kirkpatrick model. And it looks like in order, if you wanted to fix it entirely, you probably would need to have some sort of replica symmetry breaking. But unfortunately, we came up short on an analog of the Parisi ansatz for figuring out what is the correct way to include all of these replicas, what is the correct replica symmetry breaking way to include all of these replicas. But it certainly looks a lot like the Sherrington-Kirkpatrick model, and the analogy goes very far.
So there was a question by Eli Jablonovich back at early on in the talk, which is saying that doesn't this paradox already exist in the classical world? Since the time of Boltzmann, we've had an inconsistency with ever-increasing entropy versus unitary evolution. What's different with black holes? Possibly that was already answered in your talk, but maybe you could say something about it.
So typically when people talk about Boltzmann and entropy, people talk about a thermal entropy rather than the fine-grained von Neumann entropy. And so in particular, I don't know of any other theory, any other phenomenon, any other system other than gravity that can take a pure state and produce a mixed state without any interaction with an external system. So the inconsistency here is a consequence not of the fact that the coarse-grained entropy of the system is increasing, or that the system looks thermal, but is secretly a pure state. The problem here is that the system is actually literally in a mixed state afterwards, and that's I don't know of anything else, that any other force that can take any interaction that can take a pure state and without interacting with another system create a mixed state from that.
So there's a question from Engelhardt in the chat, which is, did I understand correctly that the new insight was to take into account the collapse of the star, and then we can get decreasing of the entropy like in the page curve because the area is decreasing?
Not quite. So the new insight was to actually use a little bit of a quantum gravity ingredient in here. So the new insight was to geometrize the von Neumann entropy in a particular way that that is motivated in some sense by the Bekenstein-Hawking formula, by the area, but at the end of the day, it's different. It's not the same as the Bekenstein-Hawking entropy of a black hole. So the new insight was saying, rather than computing the von Neumann entropy using minus trace rho log rho, we're going to compute the von Neumann entropy using the quantum extremal surface formula, because the ADS-CFT correspondence tells us that that formula is that surface computes an entropy which is unitarily evolving.
So I think there's a closely related question in the Q&A actually, which is, if we abandon the semi-classical calculation after the page time, why do we rely on its geometrical and semi-classical picture?
We certainly do not abandon the semi-classical calculation after the page time. I mean, if we were to abandon it, then we would just say that, oh, there's a reason why effective field theory breaks down. But after the page time, there's no reason to expect that. There's no reason to expect strong quantum gravity calculations, strong quantum gravity effects to kick in after the page time. So it's true that we have two different semi-classical calculations that we can do that give us two different answers, but we know which answer comes from quantum gravity. And so that's the answer that we know is correct. But that doesn't mean that semi-classical gravity is not valid after the page time. It takes a while after the page time for semi-classical gravity for us to say that quantum gravity needs to start making strong modifications. I mean, when a black hole is very, very small, we do expect that quantum gravity comes in, but certainly not at the page time.
Awesome. Okay, let's see. So there's a follow-up by Neil, which is just asking, so how do we get the decreased entropy? I guess it's just coming from the fact that you're doing a different calculation when there's a new quantum extremal surface, and that has a generalized entropy that's going down rather than going up.
Exactly.
Maybe Netta, do you have anything to add to that?
Nope, that's exactly it. That's what I would have said.
Okay. Let's see. Okay, I had a question actually. So you said a coronavirus mass black hole would just be around room temperature and pretty warm. Would
yes, are you going to invoke some conspiracy theory, please?
No. As much as I'd like to. No, I was just gonna ask, do you know what the evaporation time for it is? Would it like keep you warm for like a long time, or are you going to be quite happy and then 2 seconds later you're going to be hit by a giant explosion?
I mean, it's extremely short-lived.
Very long. Is it? I was trying to do the calculation on my phone during your talk, and I think I got the answer is reasonably long, but I could be wrong.
Well, it depends on what time scale. Let's see. So it's if it's coronavirus size. I'm trying to. I did this calculation when I wrote this talk, right? Because I was like, oh, how large is the, it's a single coronavirus variant, and let's see. I remember thinking that the mass is approximately that of the Everest. I think I remember I got that number and I thought, okay, this looks like that's approximately the mass of this black hole. So yeah, you might be right actually in terms of time scale. Yeah.
Yeah, scenario is taking
long time in our standard. That's right. Yeah.
Yeah.
I think that's right. Based on the it's Everest
the thermal
mass.
time is
Yeah.
the thermal time is already very short because 300 Kelvin is quite hot, but the evaporation time is the thermal time times the entropy, and I think the entropy is still large enough that it ends up big. But
I think you're right. That's interesting. Maybe we should look around for those.
Exactly. You just have a little black hole, keep you warm indefinitely. Okay. Any other questions appearing? Now is your last chance, people. So if you've been staying quiet, but you secretly have something you're dying to ask, then please do. Oh, people have raised hands. Shout out loud if you can, or anything else if you actually have questions. Let's see. Okay. I think there are questions being written. We'll give 30 seconds to let.
I think so. There was the sort of like, don't close the talk just yet. I've got something to ask. Yeah.
It's okay. You don't have to write.
Yeah, we'll wait. I promise.
Time. We will wait. Gonna close it.
We'll wait longer than the time scale of a coronavirus sized black hole. Do that. Right?
I think we will.
Maybe not.
My calculation right. I got like 10 to the 50 seconds or something, and we're not waiting that long. But I could be completely wrong. Don't worry yet. You have plenty of time to type. We will wait around. Anyone who is bored waiting can leave, but the talk will not end until we have a chance to get the questions.
Is it possible to let the participants ask the question verbally?
I don't know. I don't know how this webinar setting works.
It is. Okay.
Yeah, can we do that? Yeah. Okay. Let's just unmute participants. Okay.
Okay, let's Raphael just typed something in.
Yeah, that's Raphael has given a nice explanation of another way to think about what is being done differently in Hawking's calculation versus in the modern calculations.
I think Raphael is asking a question.
Yeah, thank you for unmuting me. So I'm still stuck on this question that we've always had this problem in physics that there's unitary evolution, and yet we know there's also irreversibility. And there's this inconsistency has existed for 120 years at least. It seems like this is yet another example, and I think you've identified many of the issues, and I know that the holographic entropy is very critical for doing that, but it seems like this is not a new problem. We've had this problem for quite a long time.
I don't agree with that statement. So the irreversibility that is often discussed is that of the thermal entropy, not of the fine-grained entropy. So in order to have irreversibility at the level of the fine-grained entropy, you have to have an evolution process of a closed quantum system, which is non-unitary. And gravity is really the only system that we know that actually does that, but it actually goes from a pure state to a mixed state. That is not to say that is not an interesting question to ask, why does the thermal entropy, the coarse-grained entropy increase? But it's a different question from asking how is it possible or is it possible for the fine-grained microscopic entropy to actually increase? Those are two separate questions. One of them is quite a bit younger than the other and is really only relevant as far as we know in the context of gravity.
Well, there are many physical systems which are isolated systems and which evolve, and then we have no clue where they've evolved to. And for all practical purposes, we've produced entropy. Yet we know at the same time, we know that that couldn't possibly have happened because the evolution had to be unitary. So that paradox exists without gravity.
No, because you're saying for all practical purposes, whereas we're talking about in principle, as Yasunori says, in principle, even if you had access to knowledge of all the microscopic degrees of freedom of the system, you still couldn't reverse it.
Yeah, maybe just to add to Netta's answer, say you have that complicated quantum system, you can do two experiments where you prepare it in exactly the same state, and then you can do what's called a swap test, where you take each particle of your two systems and you measure and do a swap measurement on those two particles, and you take the products of all those measurements, and you will always get one. As long as you've prepared the systems in exactly the same way and kept good enough control over them, then you'll get one every time, and that's the signature that the fine grade entropy is increased.
I know, but the problem with what you're saying is you're assuming you can prepare two identical systems, and that's really the essence of the problem. We can't prepare two identical systems with the level of accuracy needed to answer this question. And let me just say what size the system has to be. If you have a polyatomic molecule with, say, 6 atoms, you're already lost. There's no way to follow its evolution.
So there are two separate questions here, whether you're talking about something that we can do practically, as opposed to at the level of the microscopics of the theory. And these are two different questions, and of course they're both important, but they are different.
Yeah, even though we can't do the experiment, we have no reason to think that the answer wouldn't be one every time.
It's the inability to do the experiment that calls into question the approach. The reality is really small systems, like a polyatomic molecule of 6 atoms, is already impossible to follow its evolution.
It's not impossible in principle. It's impossible in practice.
No, it's impossible in principle. And I'll tell you why. Very small systems rapidly evolve in such a way that would require all of the entropy, all the information content of the universe would be insufficient to track even a relatively small system. I say this is a very important problem. It's important for black holes, certainly, but let's not pretend that we've even solved it for simple things like polyatomic molecules.
I think we should maybe there's someone else with the question, so we should probably move on. But I agree with you, yeah, and I agree with you the problem, but I do think it's a slightly different problem. I think Netta, you'd agree with that problem. Ed Stress, did you have a question? Okay, there's a question in the Q&A, which is how the semiclassical calculation could give you the corrections to the unfold description. It sounds magical. Do you feel the same?
Yes, I think it sounds magical. I'm stumped. I mean, okay, so I'm not totally stumped. I mean, we have the gravitational path integral, but that's really another way of saying the gravitational path integral is magical. And I agree with that statement too. But it's surprising. It's a mystery, and I guess we're looking forward to solving it.
Okay. Well, I think on that happy, excited note, maybe we should thank Netta one more time for an absolutely wonderful talk. And yeah. Oh, there is one more question. Okay, we'll ask this last question. Naive question. Other than being extremal in equations, does quantum extremal surface have any intuitive physical properties, like an event horizon traps light?
Yes and no. So let me give you an intuition from a classical extremal surface, and let's just do a cop out and say that a quantum extremal surface is a quantum version of that. So a classical extremal surface is a surface where if you fire light rays from that surface, essentially in any direction, the cross-sectional area of those light rays will neither expand nor contract. So this is very similar to the trapping of light, where if you have a sphere and you imagine you fire some light rays from it, then they'll expand as they move away from it. You get progressively larger spheres. But if you take the same sphere inside of a black hole in a situation where space-time is very heavily curved, then the light rays will actually be decreasing in cross-sectional area as they move away from the sphere. And an extremal surface is in some sense something that's in between those two, where if you fire the light rays away from the sphere, they will neither increase nor decrease in cross-sectional area. And that's sort of like what we call it as a classical extremal surface. A quantum extremal surface is, well, it takes the area plus the entropy, as you might have guessed. And that's the intuition behind these quantum extremal surfaces.
Okay. Well, yeah, thank you so much, Netta. It was really great to have you, and hopefully we'll be able to welcome you to Berkeley in person sometime.
I hope
in
so.
The future.
Yeah, it was my pleasure.
Thank you very much indeed. I will end the meeting. How do we do that? End webinar.